So this is problem 4 of week 3. It's called cuts, and the problem states that we have this chunk of wood, or this log, and Helen wants to cut this log into n different pieces, or make n different cuts. And those cuts have to be in specific places. So in the example, this log is length 100, so this is 100, and she wants to cut it at 25, 50, and 75. And when you cut a log in a certain place, it doesn't matter where you cut it, it's going to cost that length of the log. So if Helen wants to cut it at this point, it's going to cost 100 because the length of the log is 100. If Helen wants to cut at this point, it's also going to cost 100. So it doesn't matter where you cut it, it's going to cost the length of the log. And so the problem is asking, what is the most cost-effective way you can make these end cuts and save the most amount of money, basically. So if you take this example, if you just take it and you cut it from left to right, if you cut this one here first, you'll cut into 2 pieces, and that's going to cost you $100. And then you'll end up having these 2 pieces here. This one's length 25, and then you'll have another length here that's 75. And then you want to cut the 75 into 2 more pieces, and that's at 50 and then 75. So if you cut it at 50 again, you'll split into 2 more pieces, and then you'll get 2 more pieces here. So this one's also 25, and this one's 50, with another cut you need to make, and that's going to cost you 75. And then finally, to make this last cut, it's going to cost you 50. So if you add all that together, it's going to cost you 225, which clearly is not the most efficient way to cut it, because if you cut in the order of 50, 25, and 75, it'll cost you 200, not 225 that we got. So we need to figure out the most effective way to cut it. And one of the key things you can note is that if you have a log and you need to make multiple cuts, so let's say you need to make a cut here, 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 and here. If you cut it here, what you effectively do is you cut this giant log into 2 separate smaller sub-problems with 2 different logs that you need to consider now. One with 1 cut and one with 2 cuts. And so this gives us an idea to use dynamic programming, because if we can find the most effective way to cut this smaller piece and the most effective way to cut this smaller piece, then we can find the most effective way to cut this larger piece. And so if we look at this logically, if we have this log and we need to cut it here, and this, let's say, multiple cuts here, we realize that the most effective way to cut this giant log is going to be, so E, we'll say, is the most effective way, is going to equal to the length of the log, because cutting it here is going to cost this length, but it's also going to take the amount to cut this first part of the log, and then the amount to cut the second part. So if we call this, let's not call this B actually, we'll call this opt. So if we want to go from, so if this starting index is B and this ending index is E, and then this index that we cut it at is I, the most optimal way to cut from B to E is going to be the length of the log plus the optimal amount for the first part that you cut, which is this smaller piece here, which is actually from B to I, plus the optimal amount from I to E. This makes sense with the dynamic programming idea that we thought of before, right? Because to get the most effective way to create this giant log, it's the smaller logs added together plus the length. And that's what we've done here. And so now we're thinking, okay, how can we improve this even more? And if you just try to do this kind of, like, you figure out you need to cut into smaller subproblems and you do it like that, your solution will end up being O of n cubed. And obviously that's not very good, and that's not the most effective way. So another thing we can use with this dynamic programming is that once we manage to figure out how much it's going to cost to cut a log, so if we found out from B to E, if we found out what optimal of B to E is, we can store that so that later on, if we ever need to find how much it's going to cost from B to E, we don't need to recalculate it. We can simply access it again in a matrix. And we'll call that matrix cost. That's the cost it takes from B to E. So this matrix will have the starting index, which is B, and the ending index E. And then for each one of those, we'll store a separate value. And so cost will initially be like infinity, right? And then, because we don't know what it is. And then as we go on, and we start calculating the cost from B to E, we can start updating the cost of each index, and then effectively we'll fill out the cost, and so later on we don't actually need to calculate anything. And so let's actually start coding this and see if we can get a better sense of how to implement this problem. So here I have buffered reader and string tokenizer, and we're going to need to input the information. So the first line that we have is actually the length of the log, and so we'll call that n. So we do int n is equal to integer.parseInt of se.next token. And then the next line that we have is the number of cuts that we need to make, and then we'll name that cut. So let's say this is length of log, and then this will be number of cuts. And then here we'll do st is going to use string tokenizer because we need to take the next line, and we're going to read it from br.readLine. And then we'll say int cut is equal to integer.parseInt se.next token. And finally, we need to start inputting this information here, or where we need to put the cut. And there are a couple ways we can do this, and the way I found that's the easiest to understand is to create a Boolean array of length n. The reason why we want to do that is, let's say we have this log here that's length 5. So we have 4 possible cuts here, and then we'll have like, actually it'll be like this. So something like that, right? And so we'll have like we'll have beginning index and the ending index. And we see, okay, so the first part here, there's no cut. So this one's false, or it's not true anyway. And then we'll go to the next one, and this one you can cut it, so you put it true. And the next one is you can't cut it, so it's a false. And the next one you can cut it, so it's a true. And you go on like that. And then you'll end up filling up a Boolean array of just true, where you need to cut it. And the reason why we want to do that is, let's say we have a log that we want to cut. I'm just creating new pages for each one because I don't want to erase. So we have a log that we want to cut from B to E. The easiest way to figure out where we should cut is because we don't know where these cuts are going to be, right? They could be anywhere. So we want to go use a for loop and go through every single possible one, every single possible index, and we only want to cut it if at that index we can cut it. And so if we have an array here that tells you at which point you can cut it, so for example here, here, and here, well, this one, the first cut, obviously, it's not a true, so we don't cut it there. The second one, it's not a true. And then when we reach a true point, that's when we realize we can cut it here, and then we can apply the algorithm. So, hope that makes sense. If not, you'll see how it works later on. So, in order to do that, at the very top here, we'll create a static integer cost matrix, and then we'll fill that up as we go. And then oh, actually, it's Boolean. Okay, I got ahead of myself. So it's Boolean, and it's going to be called places to cut. And so this is how we're going to keep track of where we want to cut and where we don't want to cut. And so we'll say places to cut, and then we're gonna take the next line. So it's se is equal to new string tokenizer. And then we're gonna say for each one of the cuts, we're going to say int temp is equal to that next number. So for example, if cut is 3, we're going to loop through each one of these, and we're going to say, okay, so this is temp. And then what we say is we say that at places to cut, at that point, at point temp, we're going to set that equal to true. We're actually going to need a, we're going to make sure places to cut isn't instantiated. And the size of places to cut is actually going to be n plus 1, because the log will go from 0 to n. So now we've determined where we're going to cut, and we can start actually coding. And if you remember up here, we're going to need another variable called cost, which basically keeps track of how much it's going to cost from index B to index E. So that way we don't need to constantly, we don't need to calculate it every single time. We can just store it. So that will be a integer matrix called cost. And we'll do it down here. We'll say cost is equal to new integer, and it's also going to be n plus 1 by n plus 1. And then we'll loop through each one of these. So I is equal to 0 goes to cost.length. And then int j is the same, it goes to cost.length. And then we say, we want to set cost of ij equal to integer.max value. That's because we don't know what the cost is going to be from starting index to the ending index yet. So we just set it equal to integer max value. And so we basically set up everything that we need to set up. And now we need to do the recursion part. And the recursion part is the part up here where we said that in order to find the optimal amount from B to E, we need to find the length plus the optimal amount from B to I, and the optimal amount from I to E. And so we'll do that as a separate static method, and we will name it best cut. You name it anything, it doesn't really matter. And then what we need is the starting index and the ending index. Okay, so what we first want to do is we first want to see if we were actually already calculated optimal B to E. Because if we've calculated it, then it's going to be in cost. And if it's in cost, we don't need to actually calculate it again. And the way we know that if we've calculated it or not is if the cost at B to E is not integer max value. Because if it's integer max value, then it means we haven't actually calculated it because that's what we instantiated it as. So we can say if cost from B to E is not equal to integer.max value, then we know that we can simply return the cost from B to E. And so this is what turns our algorithm from O(n) cubed to O(n) squared. Because now we don't need to constantly calculate the value, or we don't need to keep calculating the cost from B to E if we've already done it before. But if we haven't done it before, then we need to figure out what it is. So what we'll do is we'll first set min cost, and this will be the most effective, or the most efficient way, or the most cost-effective way to cut a piece of log, right? And at first we want to say it's going to cost infinite amount, and we'll decrease that as we go. And then what we'll do is, for example, if we have a log, let's say this is a log that we want to find the best cut of. And there's a bunch of different places where we can cut. What we want to do is we want to loop through every single index until we reach a place where we can cut. So that's going to be a for loop. So we go for int I. We want to start at the beginning index and end at the, supposed to be an E. And then end at the ending index. So if we start int I is equal to B plus 1, then I has to be less than E, then I plus plus. And so we loop through them, and then we know that we've reached a point in which where we can cut. If at this point, our Boolean array places to cut says that index is true. The reason why is because up here we said that at the points where we can cut, we're going to set it equal to true. So we loop through every single possible index, and we say that if places to cut at that index I is equal to true, then we want to use the algorithm that we found up here. We know that int temp cost is going to equal to the length of that log, which is actually going to be e minus b, because it's the ending of the log minus the beginning. And then we also need to add best cut from the beginning to the index plus best cut the index to the end. So this line here is basically this algorithm here. L is basically e minus b. Best cut b to I is optimal from b to I, and then best cut I to e is optimal I to e. And so after we've set what temp cost is, we want to check to see if this temp cost is less than min cost. So we say if temp cost is less than min cost, so we want to set min cost equal to temp cost. And we can't just break here and just keep going on, because if we look at our example, like for example here, right? Cutting here might not be the most effective way, or the most cost-effective way for this entire log. Because if we cut here, the sum of this plus this might be 110. But if we cut here, the optimal amount for this plus this could be 100. So we want to keep going. We want to keep going and find every single possible place where we can cut and determine the most cost-effective way. So we loop through every single possible index from b to e, and we say that if we can't cut it, we'll cut it, determine the most cost-effective way to cut it there, and then if that cost is going to be less than the minimum cost that we currently found, then we're going to set that equal to it. And so, finally, we're going to need to set cost from b to e equal to that min cost. And the reason why we want to set it equal to that min cost is because later on, if we need to calculate best cut from b to e, we don't actually need to do this part anymore. We can just simply look at this top part because we have b to e, and b to e is no longer max value. And we can just simply return it without calculating it. So this line is what also makes it OM squared. So this is extremely important. And finally, we want to return min cost. And there's one thing we're missing here. And the one thing we're missing is a special case, which is if we have a log from B to E that has no possible places to cut inside of it, well, then when we go through this, min cost is never going to be updated. So it's always going to be integer.max value. And that's not what we want. Because if there's no place to cut, but we don't need to cut it at all, and the cost is actually 0. So what we say up here is that if min cost hasn't been changed, or if min cost is still equal to integer.max value, so we actually want to set min cost equal to 0. That makes sense, because in the example where we cut 25, 50, and 75, when we cut here, this part here, we don't need to worry about it anymore, because there's no place to cut, so it simply gets set to 0. And so that covers all the cases in which we should cut it. And so finally, we'll return min cost. And from here, it's pretty trivial what we need to do. We say int answer is the best cut from the beginning, which is 0, to the end, which is n. And we don't need to do anything else because everything else is done inside this recursive algorithm here. And it's also done with the dynamic programming matrix that we did. And so after we're done, we can simply output the answer. And so just going through it again, this is the recursive method that we use. This is if it's already stored, if we've already calculated best cut from B to E, then we don't need to calculate it again. So if we've already calculated else, if we haven't, then we actually need to calculate it here. Then we say, if there are no places to cut, then we simply set it equal to 0. And finally, update DP matrix, and then we want to return the minimum cost. And so here, this is where we output the answer. And then if we run this code, we pass the test case, and then we can submit it. And then we'll see, if we go through all the test cases, all of them are correct.